So I'm going to get started here. We're looking at exponential functions, and what we're going to look at are any power function. So f of x is some base to a power, and the related inverse function where we have a log of the same base to x. And we're going to look at the relationships and the models that get used for these. And we kind of want to think of some of the rules that are going to come into play for us here. So the rules I want to put up, and that way I can flip back to them periodically. Putting these up here. Let me just show you what I'm doing while I do this. So I'm listing all the rules of exponents and their related exponent rules, because we're going to come back to these rules over and over again. These are our power rules of exponents, and they have similar log rules. Log 1, 0. Uh-oh, came near the microphone there. Sorry. Let me just get my log rules here. And then, let's see, I want this side of it, so B and then there's the inverse rules. Let's see if this is still, yep, this is still showing on the screen. Log of some base of base to a power gives you x, and some base of log base of x gives you x. And you'll find that these are the magic sauce that we're going to refer back to. So I'm going to keep those up here so I can get back to them easily, since Blackboard's going to be off to the side, different from the electronic Blackboard. But what I do want to point out is we've had these exponent rules, started very early on with the exponent rules and how exponents work. And because the log is the inverse of an exponent, there's a similar form to these rules. And so as I add these new rules in, I think of them in their exponential form, in their log form. And so if we have an addition of powers, that came from a multiplication of the same base with powers. And here I have logs adding turn into a multiplication. So because a log is an inverse of the exponential, we want to be able to see these go through. Oh, kind of neat, disembodied hand. Guess I have to, yeah, there we go. Of course. But I have these up here. I'll come back to them periodically, because these are the rules that we base everything off of when doing logs and exponents. But for right now, I want to look at this relationship between these two things and look at some particular models. we have seen the doubling time and half-life time. And so we're going to start with half-life. Let's see here. Log. Yeah, I'm gonna look at some particular models and move into how these rules go together. But the first thing I think I want to do is I'm going to take these rules and show the usefulness for them for logarithms in general, and how this magic sauce here and this particular function where n times log base b of m is equal to log base b of m to the n can help us, and it can help us do something that we've had a problem with. And so I'm going to talk about your logarithm being the inverse. So we have the log base b of some function is the inverse. Now your calculator only has two keys for these. You have an ln key. I'll keep it going left to right. So if I have e to the power, its inverse logarithm is ln. Its inverse function is ln of x. And this is saying underneath the hood that this is log base e. And this is called the natural logarithm. And then 10 to the x is log with no base written. And underneath the hood, that's log base 10 of x. And that's called the common logarithm. If you watched lately, there's been some things that have been using a log scale, which means each line on the graph is a power of 10. So if you're having a graph like this is 10, this is 10 to the first, this is 10 squared, this is 10 cubed, and so on. And that's called a log scale because each jump between here gets 10 times further, 10 times further, and it's actually a log base 10 scale. And they're actually quite common scales when dealing with exponential things because if you look, I posted a video for a question on one of the homeworks which asks to find the intersection of the function 1/2 to the t divided by 5,700 when that intersects with the line is 0.16. And it asks you to do it graphically. And the problem is this function 1/2 t to the divided by the 5,700 is hugely sloped. It looks like a straight line near zero. In fact, they intersect somewhere in the 15,000s. And so when you're looking at it, this is so steep. This rise is so fast that when you're close to any part of it, it looks like a straight line. And log scales were invented to kind of straighten these curves so that you didn't have that problem. But you have to realize everything goes by base 10. And that's from the common logarithm. It's commonly used log. But your calculator only has two keys for them. And the nature of that is, I have b to a base and log b, the base. I can have an infinite number of bases. And before calculators were invented, when people had to do these things initially, they needed to do them through printed tables. And having a resource that had the answers already printed, they would make these by hand because getting the inverse function to a level of precision took you doing the calculation in one direction and then swapping your range and domain. Because of that, we can't print infinite books yet. The internet's getting us there, but we can't. And so there were common numbers used, and the natural logarithm e you'll find I use a lot because E as a function has some very unique calculus principles that make it very, very useful in many different fields, and especially differential equations. So a lot of answers to differential equations, we use the function. We'll have some functional form of e to the x in it, whatever is around it. And because of that, the natural logarithm is very, very extremely useful. It's actually a large reason this is taught at this point in time in a function/algebra class. Is if you take no other mathematics, you're going to be dealing with exponentials and logarithms from a functional use. The answer is supplied somewhere, and you're going to have functions that use these things. So it's good to have an understanding of them themselves. If you're progressing further in mathematics, the exponential and the natural exponential with base e is probably one of the most useful things you can exploit. There we go. So we only have two keys on the calculator. So there comes a problem of what happens when you want log 2 of 58. You have no way of getting the answer with the calculator. Now, some of the more expensive models and some of the computer software, you're able to specify the base, but most computer software will use the natural log exclusively, and you might have to do some different keystrokes to get the common log. So how do we trick the calculator? And we're going to go back to these rules. Here, we're going to use these rules of logarithms. I'm actually going to put a dotted line between the exponential rules and the logarithm rules, and then these are our special ones. Special ones are going to help us get through, but we're going to use these rules in tandem with these to let us solve. And it's going to show us what's going to be known as our algebra with logarithms. So I'm going to make this in a very generic form. I'm going to say that I am going to have some answer is equal to the log of a base that I do not have a key for on my calculator. And I'm going to put into that my functional value of x. Now I want to do a trick here. That is the trick in algebra, and you hear me, I say it ad nauseum a lot. Whatever I do to one side, I do to the other. There's a neat thing we can do. And I think I'm going to particularly go for the natural log first, and then I'll show you this with the common log. But if I have x is equal to 5, it's fair to say that e to the x is equal to e to the 5. Look at that for a second. X equals 5 is a statement. I'm making that. If that is true, if I take e to the power of whatever this is, that would be the same as e to the 5th. Substitution tells me wherever I see x, I can put in 5. It also tells me wherever I see 5, I can put in x. And so this equality holds true. So we can look as the function e, the base of the natural base, as being an operator. I can do the operation of taking this side as a power to e. It could also do something similar. If x equals 5, I could say the natural log of x is equal to the natural log of 5. Because whatever I have for x, I could replace with 5. My equality would stand through. And so these functions can work as operations. If functions hold true, whatever I spill into them gives me one answer, which is what we made our functions do, right? For each x value, we get only one y value. Then whatever I put in here has to equal if this was true. So I'm going to use that to my advantage. I'm going to say, you know what? I would prefer to see this. In fact, I'm actually going to be a little more trickier. I think I want to take it to base b. I'm going to b to the y equals b to the log b of x. I like that better because that's going to let me do the trick here. Let me get to my switchy. Right? If I have b to the log base of b of x, they'll cancel back out. I'm using the inverse property to be able to cancel and move things forward or backwards. So what I'm able to do by forcing this, and I can use that inverse property, I've changed my left-hand side to an exponential. And this bit here, because it's an inverse, leaves me with x. I've really written my logarithm in what we're going to say is exponential form for the logarithm. Yeah. So I'm going back to the rules that we have for logarithms. The rules, they actually give you your textbook page where these rules are screamed at us. They're on page 458 for the logarithm, the rules that we're using. All right, well, if I'm free to take something to any base, I'm also free to take any logarithm. My calculator only had two log keys, natural log and common log. So I want to take the natural log of the left-hand side. Notice my wording there. I'm taking the natural log of this number. But whatever I do to one side, I do to the other. So I'm now using my logarithm as a function, a functional operator, and I'm exploiting its properties. Whoops. The next property I want to explore is this power here. I have now made it so that I have a logarithm to a power, and that power was my variable y. Well, the other side of this equation says that that y can come out in front of my logarithm. And so here, I'm going to use that power rule. I'm going to put y ln b equals ln x. Notice what I've done. I've done this odd trickery where I no longer have the log of the base that my calculator doesn't have a key for. Right? All my logs now are in terms of what my calculator has a key for. And here I was stuck with my variable in the exponent. By taking the natural log, this multiplication rule lets me pull this down. And we're going to find we exploit this a lot when we need to pull powers down. We'll take the natural log or the common log or a log of some base of what has our variable in the power. And that multiplication rule will let us pull it down. Well, now I'll divide both sides by the natural log of b. And we get what's called the change of base formula. This y is still equal to that y. I initially started with a logarithm in a base that my calculator didn't have the key for, and I have an answer in terms of a base that my calculator does have a key for. Notice my original base becomes in the basement of the fraction, and the original term is up here. Well, what if you can't find the natural log key? So I'm going to take all my steps down to here, and I'm going to change over to a pinky color. I'm going to come back with the b to the y equals x, and instead of taking the common or the natural log, I'm going to take the common log. I'm just going to say, hey, I'm going to take log base 10 of b to the y to this side, and whatever I do to one side, I do to the other. So I take log base 10 of x. My property of logarithms doesn't matter what the base is, so this y still multiplies back out front here. And I'll divide both sides by log of b. And I have my change of base with log base 10. In fact, the general change of base formula, bright red here, is, nope, bright red ain't working for me, green, not sky blue. My y value is equal to the log of some base I have on my calculator. I'll get the log in some base I don't have to some value x. That is equal to what I have on my calculator, x, over what I have on my calculator, what the original base was. Now I know the calculators have these two keys, ln and log. So I use them specifically. Well, let's look how this works. I want a very common logarithm that comes up. Let's just do log base 2's happen a lot. So if I want log base 2 of, well, we're counting by 2's, let's go with 15. And I go over to my calculator. You'll notice here, right, on the calculator, let's see if I can get this. Let's see if we can get the keys in. There's the keys. I've got two log keys, log and ln. Right? But I don't have a log base 2. No log base 2. So, sorry about this. There we go. Sorry. And no log base 2. So, if I want to do a log base 2, I've got to change into one of the two keys I have. So I use this formula I figured out, because we're clever eagles and we used our change of base rule. So log base 2 of 15 is the same as the natural log of 15 divided by the natural log of 2. Well, let me do that on my calculator. So ln 15 divided by ln 2 is 3.906.891, and so on. Make that an approximate. I'll just leave it there. But Jeff, you said it was the same as log base 10. Well, let's do that. Let's enter that on our calculator. Let's enter log 10, 15 divided by log 2. So I hit the log key instead of the ln key of 15, and I divide it by the log of 2, and lo and behold, I get 3.906891. So our change of base formula works for us, and it works no matter what base we choose. You will find I run to ln. When in doubt, I run to ln. All right, so what we want to do here is we want to develop our function algebra and use it to build some models using these things. So we kind of want to use these properties to help us out and develop the different mathematics we can do using these function rules. And so a lot of the times we find ways of expanding expressions or taking a logarithm and breaking it apart into pieces. And I'll kind of give you a why. I'll show you some examples and we'll go why. So again, the rules that we're going to keep coming to are these over here. When I have log of 1, it's 0. When I have log base b of b, it's 1. Log base b of some number plus log base b of another number is the same as the log of the two numbers multiplied. And any rule that we have is reversible. So we're able to move these rules backwards and forwards. So let's show you what I mean. So I can be given some log of x times y. Well, my rule of multiplication, log m times n, says it's the same as log m plus log n. So that's the same as log x plus log y. And you're like, well, why? Why would people do that? Well, this is log base 10, right? So if I had log of 150, right, I would have to go and calculate on a table what log 150 was. But I can notice that 150 is the same as 15 times 10, which means log 15 plus log 10. But this is base 10. So this is the same as log of 15 plus 1. And what this allowed people to do was figure out patterns. As your multiples of 10 kept going up, you kept adding ones onto it. And so you wouldn't have to make a table or a value for each number. And this leads to some quick calculations you can do, especially when you're using log-based things like pH values. And you're learning to count the number of whatever your base is coming across here. And so this is how this rule tends to get exploited. But sometimes some of our algebra comes through very oddly. So some of our algebra might create an expression that we need to simplify like this. Let's go here. So I'm going to have log of the cube root of x divided by the square root of k. And this comes back to my pet peeve. I do not like this notation for writing roots. We're stuck with it. Hundreds of years of it. We can be the generations that change this, but it's the same as saying x to the 1/3. And I like the 1/3 because I get all my exponent rules with it. And log of k to the 1/2. Fractional exponents are so much better than radicals. That said, I'm going to use the division that's happening here to write this as log of x to the 1/3 minus log of k to the 1/2. Then I'm going to use my power rule, and I get 1/3 log of x minus 1/2 log of k. And people, when they were doing their mathematics, did these to get rid of having to take square roots. Right? They could turn them into a multiplication by a half. The whole purpose of logs and log calculations were set up so that mathematics could get easier for people for certain higher level things, powers, square roots. But you had to have a table of what your log values were. So you pushed all your problem into having the table here instead of having to do cube roots. Well, if I know what the log of the number is, I just take a third of that. And that's the utility of this type of expansion is our algebra might give us something like this. Now, calculators have made it slightly easier for us to do some of these because the calculators take the formulae for us and answer them out. But one of the things about expanding and collapsing logarithms that will be very, very helpful is that it saves how much you have to type on a calculator. So this one here, log, and then you have to hit this key, put the 3 in, x. Make sure you get your parenthesis, exit out of here, and exit back to here. But before you exit that parenthesis, you have to hit your division key, then your square root key, then your x, make sure your right arrow, and then input in there, right? And so one of the things is as your function becomes a little more complex to type in, you have to watch your grouping symbols on your calculator. And simplifying, expanding these expressions can avoid error, and they can help put it into chunks. Also, if your logarithm's coming out of a physical system or is going to go back into an exponential system, there are chunks of this that will fall through. So the skill of using these rules is much more useful than it appears. But I think any new mathematical operation, the utility comes the more you do it. All right. So that's called expanding. When I take one logarithm and I take its parts and crunch it out. Well, the opposite can happen. We can express a logarithm in terms of one function. And here's a good example of that. I have the natural log of 2e plus the natural log of 1 over e. So I have something that's somewhat expanded out, and I want to condense it down. I want to make it smaller. Well, addition tells me that I have multiplication going on. So I have ln 2e times 1 over e, or the ln, and I'll put these in parentheses to realize it's the natural log of these two things multiplied. The e's cancel, and I get ln of 2, which is about 0.69-ish, I think. 0.68-ish. It's halfway up a curve. 0.693, yeah, 0.693. Sorry, knowing kind of where about these things are can be helpful. All right, let's look at a couple more compressional forms of algebra. So log base 10 of 5 plus log base 10 of 15 minus log 3. Well, we can do this a couple ways. I'm going to take the additions as multiplication. So I'm going to get the log of 5 times 15 minus the log of 3. But the subtraction And again, I'll go back to this here. Subtraction, log base m minus log base, log base b of m minus log base b of n is the same as dividing m and n in the same base. And that is parallel to this exponential rule that we had. So I can take the subtraction and turn it to a division. So log of 5 times 15 divided by 3. And now this is all trapped in my log function. The 3 and the 15 cancel, giving me log of 5 times 5, or a log of 25. I think technically, right, that's 5 squared. I think people would see it as this because this would be easier to look up in a table and multiply by 2. But when you want to collapse it down to one term, that's probably the better answer. And so there is an algebra we do with these things. There are properties of logarithms that let us do algebra with them. And they actually help us when we work with our particular models that we're going to get out of these. But let's look at the algebra that comes about from these. So we've been doing them with certain numbers. We're going to pool all of these into particular models. But let's first work on the algebra of this. And I actually think I'll use a model for it because I use this a lot. So one of the things that I said when we were looking at a doubling model, and I'll actually do radiation. I'll actually do 2 exponential models. I'll compare 2 exponential models that are similar, and we can see the utility of this thought process. And so 2 exponential models. Growth and decay. So for the growth model, I'll think of having one cell that splits into 2, or some population bit that splits into 2. And the length of time for that is the doubling time. So for right now, just call it T double. It's a doubling time. Now the other thing that can happen is I could have a radioactive substance or something that is decaying. And so these will break down into lesser components, so they'll leave the group. And so we'll say when they break down, I'll just put X's on them, and that'll leave me with 3 things. And so there's some time where I get half, and we call that the half-life. And these models are very similar. Now, when we first model them, I could say, hey, this can be some function of my initial amount times 2 to however much time passes divided by the half-life. And that's a good model. To take everything to the power like that is a good model. Problem is base 2 can be hard to work with. This model over here, when we first look at it, and actually I'll put, you know what, I will change, since this is growth, I will make this G, function G for growth, right? We'll name our function to help us here. So this will be function G for growth, and this will be function D for decay. And I have some original amount of substance that gets multiplied by 1/2 to the power of how much time has passed divided by the half-life. And that's a good functional model for it. But 1/2 as a base, we don't have as much tables for. Well, there's a couple things I can notice here that might help me here. Both of these start with an original amount. And I'll put 2 to the t to the... So growth, and nothing I'm going to change here for growth. If I want to make decay look like growth, wouldn't it be nice if I could turn this into a power of 2? Wouldn't it be nice if I could turn that into a power of 2? Well, what is 1/2? 1/2 is 2 to the negative 1. So I could say this is a to the 2 to the negative t divided by half-life. Well, this is nice now. Nicer, right? Let's notice these things are kind of sort of the same now. Kind of sort of the same. They've got the same base, and the only difference between t divided by the doubling time and t divided by the halving time is the sign. So models of growth have positive exponents. And models of decay have negative exponents. Well, that's good to know. I'm definitely having less things to memorize as I go through here, right? Remember me, I don't like memorizing things. And so if I can use the same form of something and the only thing that changes is a sign, that makes me happy. That means when I have a word problem and I'm looking at it and my money is growing, I don't go, well, what was the equation for interest compounded continuously? I go, that's exponential growth. So I'm going to have a base to a positive exponent. When I'm looking at a bacteria growth rate, I'm going, that's a bacteria. That's growing. So I'm going to have a base to a positive exponent. And now I've gotten rid of having to pick and choose equations based on what I'm dealing with specifically, and I can look at what is changing with the thing I'm looking at. I can focus on the change, the growth or the decay. That's why exponential models are really useful for that. They strip things down to their base. All puns intended. And that's what I'm going to focus on next between these two. Well, base 2 is something I do not have on my calculator. So I'm going to say, you know what? I'm going to make a capital G for growth model. And I'm going to take it times some, whatever my initial amount, as E to K times T. What I'm going to do is I'm going to hold all of the special magic into K. K is going to become a constant. That includes the time rate. So I'm going to make K hold all the information for me. And this is what most mathematical models do. Well, instead of using a different base for everything, when we first learn it, we'll say, I've got cells and they're doubling, so I'll take 2 to some power. But at the end of it all, we'll end up using E to some constant times T. In fact, I can say this for both growth and decay, and all I have to do is add, if K is positive, it's a growth model. And if K is negative, it's a decay model. So I've taken what the book lays out is about 12 different equations for different models, and we can break them into one pattern that gets repeated depending on how the thing we're looking at changes. So our only problem then becomes finding K. And that's not too bad. Um, Before I came to the Mount, I went to Southern Vermont College, and in the one of the big groups of cohorts they taught was business people and people in the biological sciences, specifically going into rad tech. So I did a lot of focus on radioactive decay. I also did population and biological growth. So I'm going to look at a couple examples of this growth and decay model, but we're going to use these rules of algebra so that we only need to remember one thing. This. We only need to remember this. And we're going to use the type of problem to figure out K for us. All right, so I'm going to do a population growth. So let me change colors here because that yellow was hurting my eyes. So we're going to look at a population growth. And I have a town that its population, I think I'm going to use P for population. P is a good variable for population. Initially is 16,400 people. Now, you might have seen me, I did this in the other class using the base 2 model. But I want to show you how we can make this work for solving for K, and so that K becomes our driver, and then we only have one formula to remember. We could know, let me get my times here, that this population doubles every 30 years. All right. You can go to the CIA World Fact Book, a couple of different demographic statistic books. There's a Data World, which keeps statistics. And the projected doubling times of populations or decay times of populations, like where I live in Vermont right now, Vermont is losing population. More people are leaving the state than being born in it or moving into it. And then so there's decay rate models for parts of the state. Where in other areas they have the growth rate due to birth cycles. It's actually a very important part of public planning. And as you've seen, our infrastructure has suffered a blow due to the change in trade cycles and activity of people. Our infrastructure is really dependent on where people are. And delivering resources has limits. And so if your area is growing and you know the rate of growing, public planning, you should have an idea of how often you need to add resource to it. So we know that every 30 years it doubles. So I can make a population model that my population as a function of time is my initial population times an exponential, and I'm going to give that K constant there, that K constant. You'll see in different books, sometimes they'll make it, you'll see a lambda or a tau, depending on which science is going. Tau is the Greek letter for T, and so it's sometimes called the time constant. Lambda gets used in radioactive ones. It's usually divide by lambda. They all have a meaning within the field. Because I'm talking about generic versions, I'll use K, oddly enough, for constant. And K, you'll sometimes see books, because of how it transitioned in, as the Greek kappa, which looks almost like a K. It has a little hook on the bottom. And kappa and constant came together from Greek. and then it fell into English as a K. And so I'll go, I'll use K for constant, and people go, oh, you can't spell. It's like, yeah, I do maths, right? It's all Greek to me. And so this is our base model. And this will work for any exponential growth or decay. We start there. What we want to do here is, first I want to build my model with my given information. And then usually the questions will say, you know, if the what will be the population in 50 years, right? So what is the population in 50 years? So we know it doubles every 30 years, and we want to know what it'll be in 50 years. So before I even calculate, I just think, well, if I double 16,400, that would be 32,800. So my answer is going to be bigger than that. Now, if it were to double twice, that would be 60 years, which is a little bit further than my 50, right? 60 is bigger than 30. So 2 times population. This is just something I'm doing in my head to kind of set boundaries. 2 times, it would double, if I double once, right? 2 times this is 32,800. If I double one more time, it's 65,600, right? If I double this. So this would be in 60 years, and this would be in 30 years. And what I'm looking for is in 50 years, so it's going to be somewhere around there. I just want to think about my problem before I dive in and start using all these exponentials. I want an idea of what's going to happen. If the population doubles every 30 years, in 30 years it'll be 32,800. In 60 years it'll be 65,600. Well, I'm looking for 50 years, so I'm somewhere in the middle of that. And I'm just going to use that as my guiding. Now I'm going to let the math tell me what to do. Well, if I double, so P at the doubling time is equal to 2 times P naught. I'm not going to put in my 16,400. I've watched a lot of students, they'll rush right in, they'll say, hey, at the doubling time, this is 16,400. They'll get a number, and then they'll do all these calculations on the number. I'm going to make it, I'm going to say, hey, I double what I originally have. So, I'm going to substitute all of that into the model I want. And what was my doubling time? It was 30 years. Here's the joy of this. Look what I have on both sides of the equation here. So I'm going to divide both sides by original population. This is a key to exponential models. If you measure the time it takes for something to double, something to have, doesn't matter how much stuff you start with, you're looking for half that. And the dirty secret about these exponentials is they're percentage generators. If k is positive, this generates things from the number 1 to infinity. We can think of 1 as equivalent to 100% of the stuff. And 2 would be 200%, right? Doubling is you have 200% of something. I kind of think of these as percentage generators. Because if k is negative, then in my half-life is when I get 0.5. And so these things spit out multipliers. Their job is to spit out multipliers of whatever's in front of them. So if you're looking for doubling, you're looking for this to spit out the number 2. You don't care what's going to sit in front of it eventually. You just want to know when this spits out the number 2. So this simplifies nicely to 2 equals e to the k, with whatever my doubling time was. And most of the time I start my problem right here. But I would get in the habit of substituting in, making sure you're comfortable with the initial amount canceling, and that you can solve for k now. Well, how do I solve for k? K is trapped upstairs. Well, k is trapped upstairs. I have some base, and k is upstairs. If I take the natural logarithm of the base I have, I'm going to get my upstairs out nice and clear. So I said these are special. These inverses are special. They're the secret sauce. This is weird. I have my over there is where I can see if this camera is working. And so I point to this and I look over there, which puts my head off the screen. I think most of the time you've seen me doing this. I should be doing this. I should be talking to you. So this base that we have and our variables in the power, to get rid of it, I'm going to take the log. I'm going to take the log. Not over there. There. Yeah, I'm going to mess this up. I'm going to take the log of whatever the base is, and they will cancel, leaving me what's upstairs. And that will let me focus on bringing the upstairs down. And so that's why I called it secret sauce. So let's do that. So we'll take the natural log of both sides, because we can do that. Well, the natural log of something to the base of the natural log cancels, and I get k times 30 equals the natural log of 2. And the natural log of 2 is a number. It's actually a number that pops up a lot. That's why I quoted it as 0.69. All right. And so k is equal to the natural log of 2 divided by 30. I now have my k constant. Sometimes, depending on the problem I'm doing, I leave it like this. This can be messy to do, so I will approximate it to a decimal. Now here's the secret. When doing things like this, keep a large quantity of decimal places. I think I tend to try to keep 3 to 4 significant figures, so things that aren't zeros. So natural log of 2 divided by 30 is 0.0231. There's 3 sig figs. I'm going to take 0.5, so I've got 5 sig figs for right now. That gives me enough room that I won't get weird rounding errors in the future, right? This 0 in front isn't significant. It's just holding place. These numbers are the significant ones. I took 5 sig figs. General rule of thumb, take 2 more than you need. And you'll find that most applications require you to take 3 or 4 sig figs. So I picked 5. I'm just trying to avoid rounding errors. All right, so I have now built what I need to build my model. So I'm going to come back here. I'm going to get the super glue out, because that's what we do with models. And so my population at any time is my initial population times e to the 0.023105 times how much time has passed. I have made an exponential model that works for the growth. And in this case, we said, hey, how much is it going to have in 50 years? So I'm going to drop 50 in there. And what did we have? We started out with 16,400. So e to the 0.023105 times 50. And so on my calculator, 16400 times second ln gives me the e key 0.023105 times 50. And that gave me 52,000. And I'll round up 67. Notice the double check I did when I was looking at this. I said, hey, it's got to be somewhere in between. It's got to be between 32,800 and 65,600. Closer to the 65,000 side because of how doubling worked. That was just my mental check on it. If I come down here, yeah, my number was good. So our model works. What's nice about this type of modeling, yeah, finding that K constant can be a pain, but it means you will only ever need to use one key on the calculator. You only ever need to type in one thing in your spreadsheet. The only thing you keep track of is K. Everything else will always look the same. Be it you're looking at radiation decaying, you're looking at a population growing, you're looking at, you can now, go work for public planning, and you can do the population model for Athol versus Gardner versus Leominster. I'm not from around here. I'm sorry, don't hate me. Worcester, right? And you can look at the different population models, and all you have to do is change K. You keep your K changed in there. You've got one little equation on your spreadsheet, and you now have a tool that will take care of whatever you're modeling. Exponentials are very powerful functions. They're used in a lot of different places, and it's easy to say, okay, I'm going to use doubling, so I'll use base 2. I have a tripling time, I'll use base 3. But it's much more efficient to just turn everything into base E. All right, I'm gonna do a radioactive decay because they're fun, and I'm gonna do phosphorus 32. And I hope we'll appreciate a small thing changes here, and that's the sign. Oh, I have room. Ooh, this is gonna be close on room. I'm gonna clean off the blackboard. Give me a second here. While I clean off the blackboard, I'll let you see the rules. Stare at the rules while I clean the blackboard. Blackboard cleaning commencing. Look at those rules. Aren't they pretty rules? They're very useful rules. Blackboard cleaning is still commencing. Blackboard is cleaned. No more rules. Oh wait, did I switch that back? Oh, I didn't leave. Here, you can stare at the rules a little bit more. Look at those good rules. Aren't those great rules? Yeah. Back to our blackboard. Alright, let's go up here. Oops. Ah! No! We don't want yellow. We're not those type of people. That would hurt our eyes. I have to scroll up to the top. I'm way down on the bottom. There we go. Alright, so we're going to look at radioactive decay. So what happens is a chunk of substance, and in this case it's going to be made of phosphorus 32. Now phosphorus 32, inside the nucleus, the protons and the neutrons, let's see, I guess I'll use colors for those. We'll make protons blue. I've always seen them as blue. I don't know why. And neutrons, I'll color in yellow, are packed tightly in the atom. And there's more than 3, but I'm not going to stand here and draw all of phosphorus out. But it's bound by a nuclear force. Nuclear force that binds these together. Because the protons are the same charge, they're pushing on each other, they're pushing away. Those neutrons actually help them pack a little bit better by getting in between them. They kind of fill out. And this nuclear force that holds this together is kind of like a rubber band. And so these are pushing out, stretching on it. And all atoms are like this. All atoms, the nucleus of the atom, internal charges are pushing it apart, but the nuclear force is holding it together. And occasionally, the nuclear force gives way, and this atom breaks apart. And the rubber band will snap, and then it'll glue back together on other parts, and this will break down. And this phosphorus breaks down into sulfur. And a beta particle. So the atom changes into another atom. This happens for everything in the universe. Everything in the universe is decaying, right? And
and working its way back down to basic particles. The processes that had to pack all these protons together, it needed to happen inside of the early conditions of the Big Bang, or inside the center of stars, crushing down these great forces tying these things together. Well, now that these atoms are free from these forces, they want to go back to just kind of being further apart, and so they break down eventually. And so every time this breaks down, this substance loses some of its phosphorus. And so radioactive decay, eventually, I only have half the phosphorus in there. Some half-life passes, and the amount of phosphorus has halved away. And so we, as a society, we use this process. We use these different processes. Again, I taught a lot of rad tech, radiological technicians. They would find different substances for you to imbibe. This breakdown releases particles and radiation. The radiation you could see. And so if you could imbibe this, the radiation would emit from where this stuff was inside of you. Helps you see inside of you, basically. But you want to do it in a way that isn't damaging and doesn't last too long. So you look for substances that have half-lives that are short. Now, phosphorus-32 has a half-life of 14 days. And that says if I start with an amount of phosphorus-32, 14 days later, I will have half of it. Notice my sentences now. We should be thinking, wow, this sounds like an exponential. This sounds like I can take my amount of substance as a function of time, start with my initial amount, and do this. Because I'm talking after a certain amount of time, I have half. And these are percentage generators. And this is going to generate a half for me. Well, for me, what I need to know is K is going to be less than 0 in this case for it to be decay. Now, I'm not going to force that. I'm going to watch it fall out of the equations for me. But the stuff is starting to decay. It's starting to decay. Well, what I have is at 14 days, A is equal to 1/2 A naught. That's good. So let's do something here. Let's jump right here. At 14 days, 1/2 A naught is equal to my initial amount times e to the k, 14 days. Now notice we're measuring time in days. Some substances, like if you do radioactive carbon dating to figure the age of something, you measure the half-life in years. It all depends on what you're looking at. Well, those are going to cancel each other out. And I'm going to, just for convention's sake, I'm going to write the 14 in front. We want to find what the K is for our phosphorus. Now, this is again in my exponential. And my exponential has a natural, the base of a natural log. So I'm going to keep pointing to this, and hopefully I'll get my camera steering technique right. I have e to some power. If I want that power to come down, because my variable is in that power, oops, I'm doing a bad weatherman now, right? If I want that to come down, I have to take the log of the base that I have. So I want natural log in front of here. That's going to let me get my variables free. Yay. I know when you signed up you didn't realize I was this crazy. I didn't realize that I was this crazy when you signed up. I didn't know you were signing up. Alright, so I'm going to take the natural log of both sides. ln of 1/2 equals ln of e to the 14 times k. But these are going to cancel. They invert each other. Go away! 14k. Now, in a calculator world, it's really, really nice. Our calculator is going to spit out a number for this. But I want to show something. I said k has to be less than 0. But I wasn't going to do anything to enforce that. And here's why. Remember, this is the ln of 2 to the negative 1. And the negative 1 can come out front. And I'll divide both sides by 14. So I get the negative natural log of 2 divided by 14. Notice how that natural log of 2 keeps popping up, the 0.619. And there's where my negative sign came from. And so I'll do this on my calculator. Now, granted, I could do the natural log of 1/2 divided by 14. I'm going to get the same thing. And I get a k value of negative 0.49511. So I have built my model. And my model in this case is my amount of substance at a given time is my initial amount of substance, E to the negative 0.049511 times T. And I have a decay model because I have a negative sign up front. Sorry, you can't see me pointing at my computer screen. I know this is a decay. This is decay. Look at that. I have watched a population of a town grow. I have watched an atom break apart into other atoms with one equation. And the only difference between the breaking apart and the population growing is the sign. All of the magic gets held in the K constant. The K constant controls the rates on everything moving through. All right. Now, bankers. We gotta love bankers. They helped invent E for us. They had a compound interest rate. So the amount of money I have in my bank is equal to the principal I deposit times 1 plus the interest rate divided by the number of times I compound my interest rate to the NT. And so A is my money, is amount of money P is the principal, which is the deposited amount, which is the amount interest is applied on. R is the rate. Normally you'll see this as 6%, but we'll write, or whatever the number is, I'm using 6%. For some reason when I think of credit rates, I always think of 6%. I think when I was first learning this stuff, this was a common interest rate. I think now savings is less than 1%. I remember as a kid, you could save between like 3 and 5, and loans were low. Now loans are what, 15, 20% sometimes. Our loans are really low too. I use 6% all the way up to 15 or 20 with like credit cards and weird things. It's always odd at how far the savings has changed. So as a kid, you used to be able to actually make interest putting money in your bank. Now you don't. But we'll write the percentage as a decimal. N is the number of times it's compounded. So if
they take the interest on your money and put it in once a year, it's n equals 1 is yearly. N equals 12 is monthly. N equals 12 is monthly. 52 is weekly. 365 is daily. Right? And you can keep going per hour, per second. And what bankers did is they said, well, what happens if I'm constantly putting the money back in, right? Or applying the interest. And what they found was that this 1 over R divided by N to the NT approaches this thing called E. And so this whole thing has what we call continuous interest rate formula. And that's your amount in the bank is equal to your principal E to your rate times time. It's an exponential function. Your rate is determining how often you're approaching your amount, and it processes your time, so to speak. And this high level financial transactions tend to use that. Definitely you tend to get this applied against you more because this makes money more quickly than compounding on other time periods. But this is becoming more of a common way. And it's actually how we discovered the properties of E was through banking. Banking in, I think, the 1600s. This question came about, and Euler kind of figured out what would happen if we kept approaching interest over and over again. And so you'll see for continuous interest problems, you want to use this formula. For anything that is compounded, you want to use this formula. And the trick is compounded, be it monthly, weekly, daily. I tried to avoid signing these, but some of the random questions will ask you compounded monthly versus compounded continuously. They'll do a comparison between the two. It's not a bad thing to do. Notice though, nothing new, right? We have an exponential times some original amount, we get another amount back out. And the only thing we need to focus on is the rate. And that's the power of exponentials. Okay. Look at the problem for that in the homework. The example in the book is good. There's one other model I want to show that exponentials get used for. And this is kind of neat. This actually falls from a set of differential equations called a logistic model, where the exponential answers come out. I'm going to draw a strange graph here for a second. And I'm going to put a blue line in the middle. All right, so this is a graph. And this is time going across this axis. So we have some starting time, we'll say time 0, and we go off into the future. And this is a population. Some population, which will be a function of time. This blue line is called, we're going to represent as C, and it's the carrying capacity. Now what happens in environment is you actually have two competing factors. You have the factor of procreation, the population doubling time. The animals in the environment are trying, and we'll say this is salmon. This is salmon in a fish farm. And so the salmon make more salmon. Right? Basic biology. Well, what do species do? You need food, water, shelter, propagation of species, right? And so they propagate, and that's an exponential model. And so starting here, there's generally an exponential curve going up of population. If I start with some population, it will want to double and it'll make an exponential curve. But nothing is immortal. The salmon are dying. Natural consequences. Also, the environment they are in can only feed so many of them. And it's actually a very complex, the food sources and the ability to process their waste, right? If you have a salmon in a salmon farm, their waste will lead up to a certain point, disease proportions go through. So they can't populate completely, right? Or infinitely. There's a limiting factor that causes a decay model. And those two models come together for what's called the logistic curve. And it tends to look like this. You have some starting, it wants to propagate, but as more and more fish get into the stream, they use up more and more resources, which increases the decay rate until the decay rate and the growth rate balance. The rate the fish are dying is equal to the rate the fish are being born. And so the population doesn't change. And that's called the carrying capacity. That's how much fish this environment can handle in equilibrium. Well, you can try to introduce more fish to your salmon farm, but they're going to die off until they hit that carrying capacity. And so these competing exponentials end up making a model called the logistic curve. And they come out of predator-prey relationships. Growth and decay models. They pop in environmental science a lot. In fact, most of the logistic curves that I look at generally deal with environmental capacity, because what happens is this carrying capacity is the ability for the land to feed a species, and the carrying capacity shifts based on land usage and environmental factors. And so these logistic curves that pop out of that, well, they end up having a solution. And so the population at any given time, at most, will be that carrying capacity, whatever the environment can handle, divided by an exponential. Notice this is a negative exponential. So as time goes on, if time were to go out to infinity, this would get close to zero, and this would reach the carrying capacity. And so the constant A and B will determine how quickly that happens, and how that relates to the carrying capacity. And so you can solve for A. Solve for A at time equals 0. So it's based off of your initial population. And then B holds the rate, just like K did. All right, I'm actually going to pick up with the logistic curve on Thursday. And that's going to be our last lecture. What will be these models that come out of
exponential functions. Really noticed I've switched over. We've done the basics of the algebra. This, in class wise, I would have said, hey, here's the homework on the algebra of logarithms and the algebra of exponentials. You have that in your homework assignment. I handed out a half decent chunk of putting logarithms together and expanding them to get practice for it. Please try to look at your homework. I know the due dates are scheduled for the end of everything, and I also know not everyone's listening as I do these. Some people are playing catch up or whatnot. But we're going to look at particular models on Thursday and kind of tie it all together to come through. And I'll pick up with the logistic curve. We're getting close to 12 here, and I don't like pushing a large chunk of time for digesting. So I think I'll do a little bit more about the banking equation and a little more about the logistic curve once we pull back out of that. All right. Be well.